The purpose of this video and the next few videos, I guess the playlist, is to talk about how a chemical engineer would set up differential equations for the investigation of a stirred tank, or the modeling of a stirred tank, perhaps. We're really trying to focus here on the mathematical thinking rather than the details of the chemical engineering thinking. So we're going to use some fairly simple assumptions that will allow us to have enough chemical engineering to keep it interesting to a chemical engineer, but not be so detailed as to distract from the math. So first, let me draw a stirred tank. So let's imagine we have a tank. It would have a liquid level. Let's call that L. The tank would have a cross-sectional area. I'm going to call that A sub C. Usually it's constant, such that the volume of liquid in the tank would be L times A sub C. And to show that it is well stirred or perfectly stirred, we draw an impeller that looks like a little propeller. And the assumption when we draw this is that the stirring is sufficiently good that everything is uniform in the solution inside the tank. In other words, if we have a solute, let's call it A, that the concentration of A is going to be constant. What I've drawn here is perhaps a batch reactor. Let's imagine A is converted to B. Let's draw a chemical reaction. So if I say A times A plus B times B, we would need B here, is going to be converted from to C times C plus D times D. And for simplicity, I'm going to assume that whenever I draw a reaction, that I can assume that the reaction is elementary, meaning that as drawn, the reaction represents the actual reaction events. In other words, A moles of A collide with B moles of B, A molecules of A, of course, collide with B molecules of B to produce C molecules of C and D molecules of D. And if I have a K forward and a K reverse and a delta H of reaction, then I can write that RA, the rate of reaction per unit volume, is going to be K forward C A, the concentration of A to the power A, times CB to the power B minus K reverse CC to the power C times CD to the power D. And the rate of consumption of A is just going to be A times R. The rate of consumption of B, maybe I should use capital subscripts, is going to be B times R. And rate of production of C, actually let me put negatives just to make it clear that those are consumption terms, is going to be CR, and the rate of production of D is going to be D times R. And the energy generation, we're not going to dwell too much on the units right now, but if the heat of reaction is delta H, then the rate of energy generated by the reaction is going to be minus R delta H RXN. The negative sign there is because by convention, a negative heat of reaction means that heat is released, which we treat as a positive energy generation. if we happen to have streams going in, so as drawn, I've drawn a batch reactor. A continuously stirred tank reactor means that you have a feed going in. I'm just going to call this F in, F out. And the assumption here is that because it's well stirred, that the composition of this stream that we draw out is going to have the same composition as what's in the tank. Now this stream, it may have Ca in and let's say Cb in. Let's assume there's no products in this stream. Ca in is not going to be the same as Ca in the tank, meaning that we have an instantaneous change in the concentration of the tank. Now, let's talk about one more thing that could happen before we actually go into modeling the tank or setting up differential equations. We could have energy exchanged, right? So let's change. In fact, we should talk about energy. Let's first say that I have cooling water jacketing the tank. So let's just say that I have a FCW in, and then T, for simplicity, I'm just going to treat the cooling water as having a constant temperature. Then, and say we have FCW. In fact, let's assume the input and output flow rates are the same. Now, the temperature of the cooling water is presumably lower than the temperature in the tank, or if it's higher, it's not really cooling water, but that's possible. So there's going to be a heat transfer from what comes in here in the tank to the cooling water. And so I'm going to say heat transfer is going to be some constant H times the surface area of contact. Notice that that is not the same as the cross-sectional area of the tank. I have not really explained what the surface area of the tank is, but if it were a cylinder, you could calculate it. It would have to be specified in the problem, times T minus TCW. And T here is the temperature of the fluid in the tank. And so this is surface area. And this is actually heat flux. Heat transferred per unit time, per unit area. We're not going to dwell too much on the units for now, but let's just talk about the basics. One other thing that is relevant here is the actual internal energy of this solvent or of the fluid. So we're going to use the following simple equation, and that is that the energy per unit volume is going to be, so energy per unit fluid volume is going to be the density of the fluid, rho, times the heat capacity of the fluid, Cp, which both of those we're going to assume are constant, times the temperature of the fluid minus Tref. Now Tref is just some reference temperature it usually ends up falling out of the math, so it's usually not too important what it is. But just so that we don't step on the toes of any of your thermodynamics professors, let's assume that whatever Tref is, that there is no phase transition that occurs. So in other words, we could perhaps pick the temperature in, T in, as the reference temperature. The fluid enters the tank, it loses some energy because of the cooling water, perhaps it gains some energy because of the exothermic reaction, but the fluid does not freeze or boil. And so we can treat the heat capacity as being constant and also the density as being constant. So what I've done here is I've kind of listed all the terms that you would need to formulate a differential equation in terms of to determine quantities such as temperature in the tank, concentration of compounds, perhaps even the liquid level, and so let's talk a little bit about how we're going to approach these problems. And in the subsequent video, I'm going to talk about how we'll talk about specific problems that are variations on this theme. So first of all, when you do balances, so I suppose I should mention that when we formulate this kind of differential equation, we're almost always balancing something. So balance, it could be energy, could be compound A, number of moles of compound A. It could be fluid mass, for example, etc. And the general equation looks like this. Input minus output plus generation minus consumption equals accumulation. So let's talk about what accumulation is. So if I have a tank, the natural control volume to choose, I'm not going to talk specifically about inputs and outputs or what the chemical reaction might be, but I'll draw the streams just to have a standard picture here. If my control volume is the tank itself, and let's just say that I am balancing some quantity F. I don't actually want to specify what F is, but what I do want to say is that when I do these balances, I actually am looking at some incremental time. So I'm looking at what has happened in this tank over a time interval delta t. And accumulation refers to F inside the control volume at time t plus delta t minus F at time t. So in other words, in a small step of time, delta t, how much has F changed? And we're also going to use the following definition. So if I now take F at t plus delta t and subtract F at t and divide through by delta t and take the limit as delta t goes to 0, so the smallest possible step, this by definition is going to be df dt. So in order to get the whole equation, we're going to need df dt equals something, right? And that something is going to depend on how much goes in, how much comes out, how much is generated, how much is consumed during this time step delta t. So the purpose here is going to be to come up with a differential equation that relates df dt with other parameters. And the next videos will pick specific circumstances and derive differential equations that could be solved in order to calculate quantities of interest for this system.